Hello everyone, my name is Kiran Nandi. I am from MIT Academy of Engineering and my roll number is 1. So, today I am here to discuss about the course CCNA2 Switching, Routing and Wireless Essential course. Here I will briefly touch on main topics in each module to give you the all the detailed concept that it is covered in this course. So, let's begin. So, here in module 1, the basic device configuration it includes the all the initial basic setup that we do in switch and routers. In switch, the boot sequence, what happens when you turn it on from the self test right up to the loading the operating system, and that is the iOS, that is. And then it covers also the basic configuration like giving the switch a unique host name, securing different access levels with passwords, like enable secret key, and the encrypting those passwords so that they aren't the plain text, setting up a legal warning banner with MOTD, and the important is saving your work using the copy run start. And we also look at the setting up the switch management using virtual interfaces, the SVIs, and configure a default gateway so we can manage the switch remotely. Also, the switch port settings like speed, the duplex, how data flows one way at a time or both, and auto MDIX, which helps with using the right cable type. And finally, the big focus is in the secure remote access, that is using SSH. It is much safer than the old telnet because it encrypts everything, including your logging. So in module 2, that it covers the switching concepts. The main job is in here is the frame forwarding switches. The frame forwarding switches operate at layer 2 and use the destination MAC address inside an Ethernet frame to decide where to stand it. They maintain a MAC address table, sometimes called as CAM table, which maps the MAC address to specific switch ports. This table is built by learning the source MAC address of device and connected to each port. When a frame comes in, the switch looks up the destination MAC address. If it is in a table, the frame goes only out that specific port. If it no unknown or broadcast or multicast, the switch floats it out to all the ports. And also we compare the switching method like store and forward, check and store and forward that checks the whole frame for error first, which is reliable but slower, while the cut through another method. Now the cut through forwards much faster by just reading the destination MAC and potentially sending bad frames. Finally, it also tells about the collision domains where data collision could happen, mostly eliminated by switches, and the broadcast domains where the broadcast travel which are contained by the routers. So in module 3, it introduces a really important concept, that is VLANs or virtual LANs. The VLANs let us take one physical switch network and let us check one physical switch network and chop it up into multiple logical networks or broadcast domains. The device in one VLAN can talk to each other but not directly to devices in other VLAN, even if they are plugged in into the same physical switch. This is the great for performance, smaller broadcast domains, and also for security, like isolating groups like HR from engineering, and the general network flexibility. Each VLAN usually correspond to a unique IP subnet. Also, we discuss about the different VLAN types like data, voice management, and the default VLAN 1. To connect VLANs between switches, we use trunks. The trunk link carries the traffic from multiple VLAN using a special tagging system called IEEE 802.1Q. We learn a basic commands to create VLANs and assign switch ports to specific VLAN. The switch port mode access, the switch port access VLAN. These are the few commands. and how to configure, and also we learn how to configure the trunk ports like by using the switch port mode trunk command. So if a VLAN separate networks, how do device in different VLANs talk to each other then? That's the inter-VLAN routing covered in this module 4. Since the VLANs are separate broadcast domains and subnet, you need a layer 3 device, either a router or a multi-layer switch to forward the traffic between them. This module looks in a three ways to do this. The first is a legacy method, that using a separate physical router port for each VLAN, not really used anymore because it doesn't scale. The second one is the router on a stick. Here you connect a router to a switch using a single trunk link. On the router, you create a logical sub interfaces, one for each VLAN, assigning each an IP address that act as the default gateway for the device in that VLAN. The third most common and efficient method in the modern networks is using the layer 3 switch. These switches can route between VLANs internally using switched virtual interfaces (SVIs), which are virtual layer 3 interfaces for each VLAN. You just need to enable IP routing globally on this switch. And further, the basic troubleshooting for these setups is also covered in this module. So in next module 5, it covers the spanning tree protocol, that is STP. Why do we need it? Because redundancy is good. We often build networks with backup links between switches. The problem is the layer 2 Ethernet can't handle loops. They cause endless frame circulation called broadcast storms, crashing the network. And STP purpose is to prevent these loops while still allowing the physical redundancy. It does this by logically blocking certain redundant paths. The HTTP operation starts by electing one switch as a root bridge. Then every other switch finds its best path back to this root bridge and marks that port as a root port. On each network segment, connecting the switches on one port becomes the designated port, and the one forwarding towards the route, and any remaining ports become the alternate ports, and they are blocked. They don't forward data, breaking the loop. So thus breaking the loop. And the switches use special messages called BPDUs to figure all this out. This takes time for HTTP to stabilize, going through states like blocking, listening, learning, and finally the forwarding states. So these all concepts are covered in module 5. So in module 6, it introduces the ether channel, a way to improve links between switches or between switches and servers. The purpose is simple. Take multiple physical Ethernet links and build them together into one logical port channel. What are its benefits? The first, more bandwidth. If you bundle two 1 Gbps links, you get a logical 2 Gbps link. The second, redundancy. If one physical link is in the bundle fails, the traffic automatically uses the remaining links. And the third is the load balancing. The traffic can be distributed across the physical links. Importantly, the STP sees the whole bundle as one link, so it doesn't block the individual physical links within the channel. And the ether channel requires at all physical ports in the bundle having the matching setting, the speed, duplex, and VLANs. And also we can configure it statistically on dynamically using the negotiation protocol like Cisco PHGP, that is desirable auto modes, or the industry standard, the LACP, active passive modes. And also we configuration involves the grouping interfaces using the channel group command. So in module 7, it's all about the DHCP version 4, the dynamic host configuration protocol for IPv4. Its purpose is to make the life easier by automatically giving IP configuration like IP addresses, subnet, default gateway, DNS servers to devices when they are connected to network. So it just gives the automatic assign the IP address automatically without us first manually doing the static input for the IP address and all the subnets. So this also avoid the manual configuration errors and saves a lot of time. It uses the client server model, the lease process called DORA. A key, the client sends a discover broadcast serves servers offer an address and the client requests one offer and the server acknowledges the lease for the set of time. So the discover offer request acknowledges is the DORA, the lease process. And also the clients renews this lease before it expires. So this module shows how to configure a Cisco iOS router as a DHCP server, including the setting up address pools and excluding the static IPs. Sometimes the DHCP server is on a different network than the clients. Since the router blocks the initial discovery broadcast, we configure the DHCP relay agent using the IP helper address, the command on the router interface facing the clients. The router can also be configured as a DHCP client themselves, useful for getting an IP address from an ISP. So these all covered in this module 7, giving the whole concept of DHCP version 4. And the further in module 8, it moves to dynamic addressing in IPv6, covering the SLAC and DHCP-v6. The IPv6 simplifies this quite a bit. It relies on the ICMP version 6 router advertisement, the array, and messages sent by router on the local network. These arrays contains flags that tell host how to get their address. There are three main methods. The method one is a slack only. The host gets the network prefix from the array and creates its own unique interface ID, each using EUI64 from its MAC address or randomly generating one. The default gateway is simply the link local address LLA of the router that sent the array. The method 2 is a stateless DHCP v6. The host use Slack for its address and gateway, but the array tells it with the O flag to ask a DHCP v6 server for other info like DNS server address. The method 3 is a stateful DHCP v6. The array tells the host with the M flag to get everything except the gateway, which still comes from the array's LLA. So from a DHCP server, and this is the most similar method to DHCP v4 also. So Cisco routers can be configured to act as a DHCP v6 servers, clients, or relay agents supporting this all different methods. So this all covered in module 8. So in module 9, it tackles the first half redundancy protocol concepts. The problem is simple. If you only have one default gateway router and it fails, your whole network loses its connection to the outside world. So FAHRPs provides the solution by letting multiple physical routers work together as a single virtual router. This virtual router has its own IP address and MAC address that host users use as their default gateway. Inside the group, one router is active or forwarding, handling the traffic while the others are standby. If the active router fails, the standby router automatically takes over the virtual IP and MAC, becoming the new active router. This failover is seamless for the end devices. The common FHRPs include Cisco HSRP, Hot Standby Router Protocol, and the standard VRRP, Virtual Router Redundancy Protocol. The HSRP uses priority values to determine the active router, and feature called preemption allows a router with a higher priority to get over if it becomes available. So these all concepts about FHRP. So in module 10, it introduced the fundamental LAN security concepts. We may face threats today, denial of service attack, DOS, and data breaches, and all the sorts of malware like ransomware, and the endpoints, the PC, servers, phone, and personal devices are major targets. So endpoint security using things like advanced anti-malware, AMP, and host firewalls is vital. The network devices like email security appliances, ESA, and web security appliances, WSA, filter threats at the edge. The access control is managed through triple F framework. The authentication providing who you are, authorization defining what you are allowed to do, and accounting logging what you did. 802.1x provides the strongest port-based authentication, often using a center radius server. This module specifically highlights the layer 2 threats that attacks the switch themselves, like MAC table flooding, VLAN hopping, and DSCP spoofing, ARP poisoning, and HTTP manipulation. We get an overview of layer 2 mitigations like port security, DHCP snooping, and dynamic ARP inspection and all. So this all LAN security concepts are covered in this module. So in module 11, here the it gets practical with the switch security configuration, showing how to implement the mitigation discussed in module 10. The port security is configured on switch access port to limit which devices can connect. So you can set a maximum number of MAC addresses allowed. Then learn them dynamically using sticky or set them statistically. You can also define a violation action like shutdown if an unauthorized device connects. The shutting down unused ports is another simple but effective step. To mitigate the VLAN hopping, we turn off automatic trunk negotiation (DTP) using the switch port mode access or a switch port negotiate to move the native VLAN away from the default VLAN 1. And the DSCP snooping helps stop roguery. The DSCP servers and exhaustion attacks by defining the trusted ports like uplinks and untrusted port access ports and the filtering DSCP messages. The dynamic ARP inspection DAI uses the information learned by DSCP snooping to validate the ARP packets, preventing ARP poisoning. Finally, to mitigate the HTTP attacks, we enable the port fast on access port for any devices only, so they connect quickly, and enable BPDU guard to disable a port fast port if it ever receives an HTTP BPDU, which usually indicates a rogue switch. So this all about the switch security configuration. And for in module 12, we move into the wireless world with the WLAN concepts. The wireless offers great benefits like mobility and easier network changes. We look at a different wireless network type from short range personal area networks, WPNs, and using Bluetooth to common wireless LANs, and using the Wi-Fi up to a large metropolitan, up to in a large metropolitan, the WMAN, and a wide area WWAN, a wireless networks. The focus is on WLAN defined by IEEE 802.11 standards. Like dot 11n, dot 11ac, and dot 11ax, which specify the frequencies mostly from 2.4 gigahertz to 5 gigahertz band. The data rates and the technologies like MIMO, multiple input, multiple output antennas are used. Essential components includes the wireless network interface cards (NICs) in the device's home, wireless routers, enterprises, access points, and the wireless LAN controllers, WLC, for centralized management. We also distinguish between the autonomous APs and the control based APs. The autonomous APs are configured individually, while the control based APs managed by the WLC. Basic antenna types also covered here in this module. In module 13, we covers the VLAN, WLAN configuration details. The wireless network operate in different topology modes, mainly ad hoc, the device to device, and infrastructure using APs. And the infrastructure mode uses building blocks. A BSS, basic service set, is one AP, and its client as ESS. The extended service set involves multiple APs sharing the same network, same name or the SSID to allow the clients to roam and into the network. The 802.11 frame structure is more complex than the wired Ethernet because wireless is a shared medium devices like use CSMS, collision avoidance, to access the channel. The client association process involves discovering APs through beacons and probes, authenticating and then associating. In enterprise setups with WLCs, the CAP WAP protocol tunnels traffic between APs and the controller using the split MAC architecture, where the tasks are divided. The proper channel management using the non-overlapping channels like 1, 6, 11, and the 2.4 gigahertz band, and the APs placement are the key for the good performance. So this all the configuration about the WLAN is covered in this module. And the next is the module 14, where it speaks about the routing concepts. The router performs two main primary functions: determining the best path to the destination network using the routing table and forwarding along that path. And the path determination involves finding the longest prefix match between the packet destination IP address and the network prefixes stored in the routing table. The routing table itself gets its information from the three main sources: directly connected networks, the learned automatically from the active interfaces, and the static route manually configured by the administrator, and the dynamic routing protocols where the router automatically share route information with each other. The default route serves as a fallback path. We also explore the route entries, which include the destination network, how the route was learned and its trustworthiness, the administrative distance, its cost, and the metric, the next hop router's IP address, and the local router's exit interface. All these are covered in the routing concept in this module. So in module 15, we focus specifically on IP static routing. These are the routes you configure manually. They are simple, secure because they aren't advertised, and don't use router resource for calculation. The downside is they don't adapt automatically if the network changes. We look at a different types: standard routes to specify specific networks, the default routes using 0.0.0/0, or which act as a gateway for last resort, and the floating routes used as a backups and the host routes for specific devices. The configuration syntax: the IP route or the IPv6 route requires the destination network and the way to reach it, either the next hop IP address, the router's own exit interface, or fully specified, or both. So fully specified is needed for Ethernet links or when using IPv6 link local next hops. The floating routes work by assigning them a higher administrative distance AD than the primary route. So they only get used if the primary route goes down. So this all about the static routing. And the next module 16 is the last module, which speaks about how to troubleshooting the static and default routes. We start by reviewing the packet tracer forwarding process, how a router uses its routing table to find the best match, determines the exit interfaces, and the next hop encapsulates the packets in the new frame and sends out. Since the things can go wrong, the troubleshooting is essential. So we need a systematic approach using the common commands like ping test, basic layer 3 connectivity, the trace route or a tracert, which map the path of hop by hop, showing where packets might be getting lost. And the show IP route command and the show IPv6 route command are critical for verifying that the expected static or default routes are actually in routing table and active. The show IP interface brief commands confirms that the interface involves are physically and logically up and up status, and show CDP neighbors details help confirming the direct connection and a neighbor IPs. The general process is to test connectivity, examining the routing tables on involved routers, and check the interface status, verify physical links, and systematically isolate and fix the configuration error. So this is all about the troubleshooting the routes. And finally, so this completes our overview of the CCNA switching, routing, and wireless essential course. It covers the essential knowledge and practical skills for managing the modern network, focusing on switch, routers, VLANs, wireless technologies, and the security best practices and troubleshooting. So this all covered in the whole entire course. So thank you.